Hi there, welcome back. Have you ever wondered how AI understand words not as a text but as a meaning? That's the magic of embedding. This is where the language meets the math. So either you are using an LLM, maybe, or you are building a RAG application, or you are building an agent, the embedding is integral part of what you're building. That's what we are going to explore in this two-part series. In part 1 of this series, we are going to understand what is an embedding and some of the basic fundamental concepts of embedding, and then different types of embedding and how to choose an embedding model. In part 2 of the series, we are going to actually train a small mini embedding model using a simple PDF document. This is where we explore how we train embedding model, how the embedding model understands the relationship between the words, how it understands the meaning. So in by end of this two-part series, you will have all the knowledge equipped to understand what is embedding, what is importance of embedding in language models or in the RAG or in agents, and what are different types of embedding models, and most importantly how you can choose a right embedding model for your use case. So with that, let's get started. So when we talk to other humans, we use words. But when machine process information, they don't understand words, they understand numbers. These numbers capture meaning, the relationships, and the most importantly, the context. So they are called embeddings. So let's see how this translation from word to meaning happens. See, you can see that on the left you have simple phrase how to bake a bread. So it's a text, something humans easily understand, but for a machine it is just a string of character. So if this text goes through what's called embedding model, think of it like a brain like encoder that's been trained on billions of sentences. The model converts this text into vector, a list of numbers. So these numbers aren't random, each one captures a different aspect of meaning. Finally, this vector is plotted in a multi-dimensional space of meaning. Here, sentences or words with similar meaning appear close together. For example, how to bake a bread will appear nearer to steps to make a dough, or maybe how to cook a loaf. So, but far away something like a book a flight to Paris. In this way, embedding acts as a bridge, turning language into something like a geometry, allowing machines to understand meaning mathematically. So that's the magic of embedding. They don't represent the word, they represent the meaning. Every modern AI model, from search engine to chatbots, to start with the fundamental idea, understanding world through the vectors. So to summarize, machine don't understand words, they understand numbers. So this embedding turns the text into vectors that capture meaning. So similar meaning lie close together in the vector space. Let's start something simple. So imagine you are searching for something like, hey, steps to make a bread. That's very human way of asking a questions. Now, if you type this in traditional keyword based search engines, it only looks for exact word matches or something similar like bread, steps, make. It actually don't understand what you mean. So you might get results like bread nutrition facts or the word bread in economics. The word match but the meanings doesn't. So it is not that you always guaranteed to get the results which you want, or maybe which closely represents what you're asking. But in contrast, an embedding based search engine on the other hand doesn't care about the matching word, it looks for a similar meaning. Now how do we get the similar meaning? This is where the magic happens. It converts both the query and document into vectors and finds the one which are close in the meaning in that space. Now you get results like how to bake a bread at home or beginner's guide to bread making. It understands that bake and make are related concepts. So this is a leap from a keyword to meaning, from counting words to understanding the context. So that's the foundation of embedding. They make search engine, chatbots, and AI assistants understand what you actually mean, not just what you say, right? So to summarize, the keyword search matches text, but a semantic search using embedding model understands the meaning of that text, not just the a keyword based search. So first let's make sense of what the vector really mean. Just don't, for a moment, don't worry about the math. Just think in a plain language. So imagine you want to describe a song using numbers. So you could measure like a tempo, energy, happiness level, right? So there are different ways you can measure a song. Oh, a song A might have a tempo 120, energy of zero point 0.9, happiness of zero point 0.8. So maybe song B could be slower, maybe not that happy, maybe it's kind of a sorrow, a sad type of a song. Now, if you plot the numbers in a space, every songs become a point, and the similar songs end up close together. That means all the songs with the tempo of 100, 120, 110, 130, they might be very close to each other, right? So that's where the vector is. It's a list of numbers describing the characteristic of any entity. It could be song, it could be some animal, it could be a vehicle, it could be anything. It is a list of numbers that is describing the characteristics. How do we arrive at? Let's see in the coming slides. But for now, just as you understand that a vector is nothing but a number that describes the characteristics of a particular entity. Now AI model do the same thing with words. The word apple might turn into number like 0.21, 0.34, 0.72 like this. But each number captures some hidden quality, whether this particular entity, is it a noun, is it edible, is it a living thing, okay, right? Is it it does it have a color? So lot of things, is it something like is it used by some human beings? So it captures every word in that vector captures one particular characteristic of the one, not literally, but we'll come to that actually. But for now, to understand what exactly is a vector, having this conceptual intuitive knowledge that a vector is nothing but a sequence of numbers related to an entity that captures the particular characteristics of a number. So just like a song gets its coordinates in a music space, the word get their coordinates in a meaning space, and the list of numbers, that is a vector. So now we understand what is a vector. To summarize, this is very important. We should understand that a vector nothing but a list of numbers that describes specific characteristics of an entity. So now we know what is a vector, which is nothing but a list of numbers representing entity, which each number representing a specific characters, or maybe just list of numbers. Let's see how this vector becomes an embedding, right? The vector has to become embedding to represent a meaning. So now an embedding is a vector that represents a meaning, not just the form. So it is created by training on billions of sentences, observing how the word appears together. For example, you are training your model on billions of sentences, and you see that the word dog often appears near the pet, maybe bark, maybe leash, right? Maybe it appears together, maybe it appears near wherever we are talking about animal, right? So now the model learns from these patterns that the dog and bark, pet, maybe our puppy, they are all related. Even though they are different words, they are all related, they are close together. That's how the embedding works. They are not assigned manually, they are learned from the context. Each number in the list encodes some abstract feature of that meaning. So when you hear embedding, think a vector that represents a meaning. So now we learn what is a vector, which is nothing but a sequence of numbers representing a characteristics of entity. Now we learned that what is an embedding. Embedding nothing but which gives you the meaning for that word, right? It is learned by training the embedding model on a millions and billions of sentences, right? Now, once the words are converted into embeddings, they exist in what is called embedding space. So you can imagine it like a giant map. Except instead of geography, this map organizes meaning. So in this space, words similar in like a dog, puppy, cat, they cluster close together. Words like car or train sit far away because they mean something different. So the model uses this geometry to measure the similarity. So when you search for the cute puppy, it finds embedding that are closest to meaning into that phrase. That's why we say embedding captures semantics. They transform the meaning into a geometry. Now that we know the embeddings and embedding live in a space where meaning is represented geometrically, the next question is how do we measure how similar these two meanings are, right? So inside the space, we don't just look at how far two points are, we look at how well they point in the same directions. The measure is called cosine similarity. It compares the angle between two vectors. If two vectors point in almost same direction, they represent the same meaning that are nearly identical. For example, you can see that in the diagram below, you have something called words like dog and puppy, right? They form a small angle, meaning that the cosine similarity is close to 1 or very high. They point in the same general direction. That's why the model know they're related. But now look at dog and car. This arrow points in a completely different direction, meaning cosine similarity is low. One is an animal, one is a vehicle. So they are not very closely related. So in embedding space, the angle equals meaning alignment. So cosine similarity helps us measure how similar two meanings are, not by distance but by direction. That's why this is the most common way AI models measure semantic similarity. So to summarize, the cosine similarity is the angle between the vector. The smaller the angle, the closer the meaning. They measure the direction between the two vectors, not the distance. So there is another way to measure these vectors called Euclidean distance. Of course, it is not as popular as cosine similarity. The in Euclidean distance there is a measured by something called a straight line between 2 points in a space. So here we are taught 2 points, dog and puppy. The shorter the distance between them, the more similar they are in meaning. That seems very intuitive. Smaller distance, closer meaning. But there is a subtle problem. Distance depend upon how long each vector is. So, but there could be something like, the vector, both vector point the same direction, but they might represent say different concept altogether. But because one vector is longer than the other, so the measured distance between them look larger even though their meaning haven't changed. That's why Euclidean distance can sometimes be misleading when comparing meanings. So it's sensitive to vector length, not the directions. So to summarize, the cosine similarity ignores the length and focus only on the direction, which make it much better fit for understanding semantic similarity. While the distance tells us how far apart 2 points are, cosine tells us how aligned the meanings are. So Euclidean distance measures how far apart 2 points are. They are very sensitive to vector length, but whereas the cosine similarity measures alignment, so better for the meaning. Now we look at different types of embeddings. To start with, dense embedding. So these are what is dense embedding? These are the vectors where every dimension carries some value, no zero, no gaps. Think of it like a tightly packed suitcase where every pocket is filled with some semantic meaning. So dense embeddings are highly compressed and great for capturing overall context. So that's why when you are building a RAG system, to do semantic search we use dense embedding. Whether you are doing a text classification or you are doing a semantic search, this is where the dense embeddings are very popularly used. Some popular models that generate dense embeddings like we know like sentence transformers or maybe OpenAI's text embedding, In short, if your use case involves finding semantically similar content or building a vector search engine, dense embeddings are your go-to choice. So other type of embedding is sparse embedding, a completely a different approach. These embeddings are mostly zero, only few dimensions light up, representing the most relevant concept for a given input. You can think of it like a bookshelf with just a few labeled books, maybe AI, math and finance. That's all you need for this particular input and everything else stays empty, right? So you are working only on these three things. So for your study research you require only three books, so you keep only three books in your library shelf, not everything else. So sparse embeddings are specifically useful for a large scale search system, and they work well with the sparse vector database like Elasticsearch. So but what is this these why these models are powerful? Because when you want to be a keyword driven representation, so for example you are looking something like enterprise scale search where the precision matters, right? That's where the sparse embeddings are really helpful. So now let's move on to something more advanced, which is a multi-vector embeddings. So unlike a dense or sparse embedding that gives you a single vector per input, a multi-vector embedding produces multiple vectors, each one capturing different aspect of the document, right? Think of it like a team of superheroes, each specializing in unique skills. So one capture a topic, another capture an entities, third handles a tone, and so on. This is incredibly useful for a multi-vector search, a fine-grained retrieval or a very advanced RAG pipeline where we need to match on different semantic layers. So if you need a rich flexible understanding from a long or a complete text, multi-vector embeddings are the way to go. Now lastly, talk about the long context window embeddings designed to handle very large chunk of text, sometimes thousands of tokens long. So traditional embeddings often lose context if the input is too long, but these model can compress and retain full document, preserving the meaning across the introduction, the chapters, the conclusion, like a building a memory a palace that stores the structure and ideas of entire document. So these embeddings are ideal for document level RAG, chunk summarization, similarity comparisons across long inputs, right? So for example, if you use case involves a lengthy PDF, a research paper, or a maybe a customer call transcript, that is this type of embeddings will really help you to effectively understand the semantics, or maybe to do an efficient search. So to summarize, so far we have learned about different types of embeddings, dense, sparse, multi-vector and long context. But how do you actually choose the right embedding model for your use case? So let's walk through 5 common use cases and see which model fits where along the real world examples. So something like a semantic search. Imagine you're building a customer support portal. A user types something called reset password and you want to retrieve the most relevant FAQ even if the text doesn't exactly match, right? Here we look for semantic similarity, and that's where the dense embeddings shine. So these embeddings compress the meaning into compact vector where, as we discussed, the closeness is equal to similarity. So you can use something like a sentence transformer or OpenAI text embeddings, or these are all different types of dense embedding models you can use it. Another use case, now let's say you want to search inside a 50-page a PDF document, maybe a insurance policy or maybe a legal contract or maybe a research paper. So traditional embedding might truncate or miss the context beyond a few paragraphs. But a long context embedding are designed to process and retain meaning across thousands of tokens. And this is when models like OpenAI text embedding 3 large will help become extremely valuable, They allow you to embed entire document, not just the fragment. So your search becomes far more context aware. Next, we'll look at the case for a multi-vector use case. Say you're building an e-commerce search engine. A customer searches, a comfortable red running shoes under $100. Now, you are not just looking for a keyword match, you want to match the intent, the attributes, the category, and even the tone if there are some reviews involved. So here a multi-vector embedding breaks the input into multiple semantic vectors, each capturing different dimension like a topic, the sentiment, or or entity. So the something like Colbert or Hyde and Tensor Lake, which offers a multi-vector support out of the box. So the type of setup work really well in advanced RAG systems, or if you are building something like a personalized recommendation engine. Now, a keyword focused a precision search. Sometimes semantic similarity isn't enough, especially in legal, medical, or regulatory domains where exact terminology matters. For example, you want to search for occurrence of a provisional patent in a corpus, and dense model might miss a keyword match. That's where a sparse embedding or hybrid approach excels. But sometimes you can use both combination of sparse and dense embedding in a typical rack systems. So and mostly sparse embeddings are used in very specialized domains, whether you are using some legal legal, or maybe some compliance platform, or maybe you want some medical terms. So wherever you require very specific, very focused domain, sparse embeddings are a great choice. So finally, if you're building something like auto tagging for a support tickets, or classifying reviews by sentiments or the topic, that's the typical text classification problem. So you just need embedding that represents each input clearly and efficiently. So for this, again, dense embeddings works well again. So typically we see that majority of the cases where you're building like a RAG, or maybe as kind of a semantic search, dense embeddings are really as a good choice for most of the cases. But in specific cases you might also consider you know um, uh, different types of embedding, like either long context or multi-vector, can be, as I told, in case of a document search or very specific domain specific search. Again, you can use a different type of embedding model. So but how do you decide? So I think the question we need to ask is, am I working with a short text or full document? Do I need a keyword precision or multi-dimensional understanding? Is this for a search, tagging, or retrieval? So once you know that, you can match the embedding type, whether it be dense, sparse, multi-vector, or a long context, to the model that excels it. So the bottom line is, the best embedding isn't the most powerful, that is the one that fit your use case best. Now that we understand what embeddings are and how the meaning is represented, let's see how this connects to a typical LLM or large language models. So inside every LLM, embeddings are the first steps of understanding. So when you type a sentence, each word or token is converted into embedding. In as with again, embedding means a numerical way to represent a word that captures the meaning and the context. So now these embeddings are passed through multiple transformer layers, where the relationship between words are learned using attention mechanism. So the embeddings are literally how the LLM thinks. But embedding also exists not only outside LLM also. Suppose if you're building a RAG or retrieval augmented generation system, every query is converted into embedding, and then we try to match these embeddings with all the embeddings you already stored in a vector database, right? So that's how the embeddings are used. So embeddings are used both in the LLMs and also when you're building a RAG systems. So now that we have seen what embeddings looks like, let's talk about how we actually use them. So when we pass a piece of text like a AI improves healthcare through an embedding model, it transforms this text into vector that capture its meaning. So once we have these vectors, we can compare them in a vector space. So if two sentences are similar meaning like AI in the hospitals or machine learning for diagnosis, their embeddings will be close together even though they use different words. So the ability to compare meaning instead of a text opens up a range of real world applications. So semantic search, which is where the most embeddings are used. Finding document that means the same thing even if they don't use the same keyword. Second, we can use in recommendation system, suggesting similar products or articles, right? And next one is clustering and classification, grouping related ideas automatically. And even RAG pipelines where embedding help find the more relevant context for the LLMs. In short, embeddings turn the language into form that computers can reason about. So before we move on to the actually building embedding model, let's take a moment to summarize what we learned so far. So we started the problem keyword search. It matches text but misses the meaning. Then we talked about vectors, a list of numbers that describe things like a song or words. Next came embedding, a special vector that learns the meaning from how words appear together in real sentence. Then we saw that these embeddings live in a embedding space, a map of meanings where related ideas clustered together. Finally, we learned how to measure meanings not by distance but by direction using cosine similarity. So in short, embeddings are how AI turns language into geometry and use that geometry to understand and retrieve the meanings. So in the next session, we are going to actually first understand how to build our own embedding model, and we are going to take a simple PDF file and train embedding model using that PDF file, and we are going to see how it can actually identify the relationship between different words. So see you again in the next session.